Yeah.
Okay, welcome for part 2 of the soil seminar today. Our second speaker is Ohene Akuoko. And Ohene is a master student in the environmental science program here at Iowa State University. And he just defended his thesis last week. So if he finishes it and turns it in by tomorrow, he's actually going to graduate. Today he's going to talk to us about part of his research dealing with surface energy partitioning. Please welcome Ohene.
Thank you. Appreciate the introduction, Dr. Horton. Thank you all for coming and being here today. Again, my name is Ohene Akuoko, and I am an environmental science master's student. And my research specifically focuses on surface energy balance partitioning in till and non-till bare soils. So today I would like to discuss and kind of see if we can answer the question of, does tillage affect surface energy balance partitioning in bare soils? So to begin, we must answer the question, what exactly is the surface energy balance? Every day we receive shortwave solar radiation from the sun, and that shortwave radiation is either absorbed or emitted at the surface. And also the Earth emits radiation in long wave forms, which is either emitted to the atmosphere, lost to the atmosphere, or reabsorbed or reflected back to the surface. And so this essentially the balance of the net amount of energy that is lost in the in outgoing radiation, and the balance of the amount of energy that is gained at the solar surface through incoming is what is known as net radiation, as you can see to the far right. And this net radiation is then partitioned, and usually partitioned into 3 main fluxes, which is what drives a lot of weather and climate cycles, and kind of determines, whether you wear short sleeves or a coat in the middle of April. And that's kind of, and the first main flux we're looking at would be soil heat flux or the ground heat flux. And this is essentially the energy that goes into, as partitioned into heating up the soil and heating up the ground, driven by thermal temperature gradients. And then we also have what's sensible heat flux, which is essentially the energy that goes into heating up the atmosphere, and driven by surface temperature and atmospheric temperature. And then finally, we're looking at latent heat flux, one most common to a lot of us. It is essentially the energy that goes in, that changes the state of liquid water to water vapor. We also notice that evaporation, or more commonly evapotranspiration, especially when there's vegetation present, as is done in most of the world. So in an equation, the available energy at the solar surface is known as, by the equation outlined here, Rn minus G is can be partitioned into what is on our turbulent fluxes that you see to the right of the equation, which is sensible and latent heat flux, and these both are usually positive in the upward direction from the surface, and G is positive in a downward direction going away from the surface. So why do we study the surface energy balance in agriculture? Well, essentially, these heat and water transfers in agriculture, agroecosystems, have a large impact and significant impact on the microclimates in agricultural ecosystems. And these microclimates then can affect the time evaporation occurring at multiple plots, affecting when you would like to irrigate the soil. Also affects soil temperature, which all influences springtime seed germination and also emergence of seeds. And then a very important microbial activity is largely dependent upon surface temperatures and also soil water contents, and which largely affects the nutrient cycling in agroecosystems. And the most important thing that it influences essentially plant growth, affecting all these systems. And so accurate modeling and measuring of surface energy balance partitioning is therefore very important to understanding how these processes operate in agroecosystems. And looking at bare soils and both density in agroecosystems, specifically a very important and a very commonly utilized soil physical property and metric is bulk density. And it's important to we understand to water flow and water dynamics, but also it is also very important to the energy partitioning, energy movement and transfer within the soil and also between the soil and the atmosphere. And usually, as being mentioned, this in most models and most measurements, it is assumed that bulk density is static or doesn't change throughout periods or throughout the season. And so, but we understand that not to be true as plant roots, machine traffic, and cropping system management as tillage and different forms of tillage, and also natural processes such as rainfall events through wetting and drying, and also freezing and thawing does affect and can change bulk density, making it more dynamic rather than static. So essentially the objective of our research then is therefore to study to quantify the effect of changing bulk density on surface energy balance components, specifically net radiation, soil heat flux, latent heat flux, and sensible heat fluxes in a tilled and non-tilled bare soil with time. And to do this, we set up a plot in Iowa State Agronomy and Agriculture Engineering Research Farm in the Clarion clay loam soil about near Boone. And our season lasted until from July 18th to October 17th of this past year, 2017. And we again use rotary tillage at our plot, and we tilled the eastern. We tilled the eastern half of our field in a north and south orientation, as you can see there. And our right side, our western half was left was non-tilled and left effectively bare throughout the season. We call it a non-tilled soil because we do know that it was tilled in the recent past, but so we can't really call it a no-till, and also there was no residue left in our soil field for the period, as no-till usually has some form of residue within it incorporated. And our fields were left perfectly bare, and we used herbicides whenever any crops such as this popped up, and kind of to get rid of those. And so in the measurement of surface energy balance components and partitioning, there's a variety of ways to measure it, but we utilize the micro-Bowen ratio system. It's a relatively inexpensive and also a relatively accurate way of measuring the partitioning through the Bowen ratio. And essentially it is, the Bowen ratio system is equipped with a net radiometer at a 1.25 meter height above the soil surface to measure net radiation at the surface. And then we also have outside of the screen and below the soil, we had a soil heat flux plate positioned at a 0.6 at a 6 centimeter depth, and above that there was temperature measurements at at the surface 2, 4, and 6 centimeters below the surface, and this allowed us to calculate the soil heat storage above the soil heat flux plate, and that combined with soil heat flux plate measurements allowed us to receive the surface soil heat flux for the measurement in G. And the micro-Bowen ratio, as you can see here, has two tubes at two different heights. The Bowen ratio utilizes tubes at sometimes heights of 1 and 2 meters. The micro-Bowen ratio uses it at a smaller scale to get surface fluxes. And these tubes were at 1 and 6 centimeter heights above the soil surface to measure atmospheric temperature and also atmospheric water vapor. And through measuring the atmospheric temperature and water vapor, we're then able to derive sensible heat flux and also latent heat fluxes to determine our Bowen ratio. And determining the Bowen ratio, we are able to, as long as we have net available energy through Rn and G measurements, we're then able to determine latent heat fluxes and then sensible heat fluxes, the residual. So in looking at our results for our season and our for this past year, I'd like to first begin with our seasonal bulk density and also water content. Again, we till the soil. The X kind of marks the date of tillage, and these tan kind of bars marks our focus periods where measurements were focused on through a drying period. These both were following multi-day rainfall events and occurred at a period that was relatively early after the tilling event, and also a period that was relatively late, to determine the effective time on on your surface energy balance component partitioning due to tillage and bulk density changes. So as you can see, at the till and non-till early in the season, there was not a lot of variation between bulk density. Bulk density measurements were made essentially after substantial rainfall events. It was pretty dry season, so substantial rainfall events didn't occur too often. So you'll see that the till and till did not change significantly early in the season. Through period one, we assume it also be similar between the till and no-till side. But we do see that during period two, there is a significant difference between till and no-till bulk densities, where our till side bulk density was actually higher, increased, and became higher than the no-till bulk density value. And in looking at volumetric water contents throughout the season, we see early in the season, if you remember, it was a pretty dry June and July this past year, and was kind of identified in our measurements. But as our measurement period began, we started to see a little more rainfall events, and our water contents follow suit in those trends. Early in the season, we see that water content between till and no-till was very similar, almost to the point where it almost mirrored each other for early in our season between the till and no-till soils. But we do see that after a substantial rainfall event on day of year 235, was also the day of the solar eclipse. If you remember, that was a pretty cloudy and wet day. That we did see now a difference between the till and no-till soils, where the till soil was now higher than the no-till soil plot, and this actually continued and remained to be the same throughout the following the rest of the season into our second period of measurement as well. So now we kind of see how bulk density and water contents were changed and affected by tillage throughout the season. I'd like to look at our surface energy balance partitioning and components with time. Beginning with period one, which was between day of year 216 and day of year 220. We like to begin with net radiation and soil heat flux values. We see net radiation and soil heat flux. Beginning with net radiation, we see that it ranged for the period between 475 and 630 watts per meter squared. These small little indentations in the curves are kind of our identified cloud cover affecting soil radiation. And we see that between till and no-till that there was essentially no difference between the two curves, between peaks or morning or nighttime values. And this lasted for the entire period, as we can see. We believe this to kind of be due to effective surface temperature, and also was similar. And also, this was about 17 days following tillage, and there was a few rainfall events that happened. And looking from notably at the till soil surface, soil was now smooth and kind of similar to that no-till soil surface. So we believe that those similar surfaces could cause similar albedos to occur, leading to net radiation values to not be significantly different from each other. Also looking at soil heat flux measurements diagonally for this period, we see that soil heat flux also was not different between till and no-till and non-till measurements. We see that throughout the entire period, except for as the soil dried, we do see that the peak value does change between at the till side actually became higher than the non-till soil for the period. And to kind of better quantify this, our soil heat flux measurements, we'd like to show you some of our thermal properties for our period, as kind of described by being earlier. So we first would like to look at volumetric heat capacity for the same period. And you can see, as being mentioned, that volumetric heat capacity in a soil is determined highly affected by water content and bulk density. And if you remember in period one, that bulk density was similar, and also volumetric water contents in our soil was similar. And our volumetric heat capacities was slightly higher to till soil surface, but we don't believe it to be significantly higher for the entire period, not to affect the soil heat fluxes within our soils significantly. And looking at soil temperature profiles for the period, we have the dotted and the solid at the top is our surface temperature, and the green solid and the orange dotted is at the bottom is our temperatures at 4 centimeter depths. And we see that the surface temperatures between till and no till was pretty much similar throughout the entire period. And you notice here also our first day, kind of where the surface temperatures and 4 centimeter temperatures were similar due to the effect of surface water content dampening the temperature at the surface. And so we see that surface temperatures were not different between till and no till. Surface temperature again is also an indicator of long wave radiation outgoing, and so we see that another kind of supporting the data that net radiation values during this period was not significantly different for the period. Now looking at evaporation, as I mentioned earlier, we measured we measured through a microborn ratio system. We also measure evaporation through a mass balance approach known as the microlysimeter method, which is essentially similar to taking soil cores and taking them and capping them and weighing them, and then putting them back into the soil for a specified period of time, and then reweighing them. And that mass, whatever mass is lost or gained, is assumed to be due to evaporation of water or gained through water. And our microlysimeter measurements of evaporation are highlighted in the dark gray and dark blue and also dark gray values. Between the till is the blue, and the dark is the gray is the non-till soil evaporation. And our light blue and light gray represents our till and non-till microborn ratio estimates of evaporation for the period. So you can see for the period that evaporation was greatest and largest during the first day of the period. As you remember that our net radiation was also very high during that day, and water content was at its highest as well. And evaporation essentially was between till and no till was higher significantly the first day at our till soil site as opposed to our non-till soil site. But as the opposing, also we can say for day year 218 and 220, this is also significantly higher at the till as opposed to non-till, excluding day of year 217. We believe that this counts to be the effect of the tillage of the soil kind of affecting the surface structure, and also a surface crush that could affect the resistance of evaporation at the till as opposed to the non-till soil surface. And this would have caused high evaporation on the first day when evaporation is in stage 1 and believed to be more dependent on how much energy is being applied to the system. And as you remember in soil heat flux and also our net radiation were similar values, so the available energy that would be applied to evaporate water during this period was similar between till and no-till soil surfaces, along with water contents. So that's why I believe that the soil surface and soil physical properties would have the largest effect of evaporation during the period. And in looking at the kind of describing all of our partitioning values, soil heat flux, latent heat flux, and sensible heat fluxes during the period based on energy, we see that again, latent heat flux is recognized in the blue, sensible heat flux is in the yellow, and soil heat flux is in the orange at the bottom. And we see that on the first day that latent heat flux, especially in our till soil surface, dominated the energy net radiation partitioning, and that as the soil dried, we see also that latent heat flux, the energy going to evaporating water, also decreased as well. We see that also on the first day of till and no-till that the soil heat fluxes were of similar value, but they were also at their lowest on the first day. Remember that soil heat flux is driven by temperature gradients, so that temperature gradients we would assume to be decreased on that period, as well as sensible heat fluxes, which are driven by atmospheric temperature gradients. And as we see, as the soil dried, the sensible and latent and soil heat fluxes both increased with time for the period. And we see that soil heat fluxes did not differ widely, but we do see in the turbulent fluxes that energy was partitioned more differently between till and no-till. specifically more energy going into evaporating water at our till site throughout the entire period. Looking at soil surface energy balance partitioning during our second period of measurements later in the season. During day period 262 to 266, which is essentially September 19th and through September 23rd, we see through 5 days diurnal net radiation and soil heat fluxes the net radiation was pretty much constant around 500 watts per meter squared per day, and we do see that soil heat fluxes were now different between the till and no-till soils, where we see that the till soil surface is now consistently higher between both surfaces. And looking at soil thermal properties affecting soil heat fluxes during the period, we see that the soil volumetric heat capacity affecting the soil heat storage measurement was we believe to be kind of significantly higher than on the till side than on the no-till side now during this period, a lot larger than what we saw during period 1. Again, during our second period, we did see a change, a higher bulk density at the till soil site and also higher volumetric water content at the 3 centimeter depth. And we also see that surface temperatures and 4 centimeter temperatures were also affected during this period, and they were lower at the till soil as opposed to the non-till soil, which is an indicator of a soil that is wetter at its surface. And looking at evaporation of water during period 2, we see, contrary to period 1, that no-till actually evaporated water at a higher rate than the till soil did during our second period, especially during the first 2 days when we believe the soil water to be energy limited or stage 1, and depending on how much available energy was occurring. And as you see in our net radiation and soil heat flux measurements during period 1, during period 2, that a higher till soil, the higher soil heat flux at the till soil caused less energy available to be partitioned to sensible and latent heat fluxes. And we see that this to be translated here, where we have less available energy at our till soil site, leading to less evaporation of water when the evaporation is energy limited. And also want to point out that during our last day of measurement during this period, that although it wasn't significantly different, our measurements, but we do see that the higher water content at the no-till soil till soil surface led to higher evaporation. We believe this to be due to after energy goes from being energy limited from stage 1, it goes to stage 2, where it's more water and soil property limited, and so a higher water content at our till soil surface would have led to higher evaporation of water during the till. And again, looking at the partitioning during our second period, we see again that latent heat flux dominated the partitioning of net radiation during this period, to the point of the first day where sensible heat flux was in a negative, as latent heat flux was evaporated, was partitioned to actually a percentage higher, 100% and more of the available energy, which believed to be caused by evaporation during this period, as or the energy brought into our system through wind, as our highest wind values were also observed during this day. And again, we see that as the soil dried, that the latent heat energy partition to latent heat flux then decreased, and that energy partition to then the sensible and latent heat fluxes both decreased with time during this period. In conclusion, we observed that a 0.11 gram per centimeter cube increase in bulk density led to 7% lower available energy at the till soil site during period 2, and this in turn led to 10% less energy being partitioned to evaporating water at the till soil. And so a slight change in bulk density affecting other soil thermal properties in our soil plot this year resulted in differences in surface energy balance partitioning with time, and also turbulent, latent, and sensible heat fluxes. I'd like to acknowledge Dr. Horton, my committee, and also lab partners and people who have helped me with my research throughout the time, and also some of our funding resources as well. Thank you, and ever any questions? Mr. Castellano?
How much of the effect on the energy balance is due to tillage versus the differences in crop residue cover on the soil surface?
Yeah, our study, we didn't look at crop residue cover, but in previous studies, the crop residue cover can have a large effect on the surface energy balance partition, depending on how much and where, if it's kind of mixed in the soil or actually as a cover. We believe crop residue would affect the albedo, a lot of crop residue kind of in a lighter hue, so it would probably reflect a lot of that net radiation initially at the surface, so you would have less energy that could be partitioned to the different fluxes of going into the ground or evaporating water and things of that nature. By a lot of crop residues, you may see lower temperatures within the soil and less evaporation occurring as well. Dr. Armbuckle first.
Could you go back to your picture of the microbial ratio system, please? So the yellow arrow is pointing to an instrument there. I think you called it a net radiometer. Is that in fact a net radiometer, or is that something else?
Yeah, sorry. I didn't mention this. It is, in fact, a net radiometer, but a neighbor sitting right next to it is we have an infrared thermometer, also measuring surface temperature, and that is the net radiometer is more horizontal to the surface, and it's kind of flat. And our infrared thermometer is right here, and that's measures surface temperature at our solar surface. And I forgot to mention that in our measurements. So that allows us to get surface temperature measurements. Dr. Cruz.
You tilled that with kind of a roller tiller, right?
Yes, sir.
How did you measure bulk density after that? That's not an easy task.
Yeah. Yes. So we actually found that out the hard way. Trying to measure that immediately after, and it was very, very fine. And so we actually decided to wait after a substantial rainfall event occurred to kind of cause some compaction of that loosened soil. And while it was wet and a little bit more compacted, made it a little bit more of a easier task to let it happen. And we were fortunate enough that it was a pretty dry summer, but during after our tillage, we had a rainfall event occur, I think 2 or 3 days following. Sorry.
So looking at your conclusion slide, it seems like there's a small increase in bulk density has a big change on evaporation. Is that right?
Yes, second. Yeah, so we saw that. So essentially the amount. 0.11 is not a large increase in bulk density at all, and we do see that just at our bare soil surface that's how it did affect the 10% for the period.
So I'm wondering, what implications do you think that may have for changes in land use going into the future? More areas are going under tillage, for example.
Yeah.
Would that have a significant impact on how energy is being partitioned on a regional scale?
That would be something to look into. I think that I don't know for sure, but I'll believe that as more tillage would occur, and as I think the main thing with the bulk density changes effects on the evaporation of waters is how it affects the thermal properties and how those thermal properties kind of allow energy to be partitioned into the soil, and also the water content allow. So I would say anything that essentially how you manage, I guess, your water content values, and also managing the soil. If you're looking at a large regional bare soil surface, I think you can have a big impact. But I think most crop management practices they're utilizing different cover crops during over the winter or crop residues which also could kind of deter any effect of a larger evaporation occurring as well. So I think those other kind of factors have to be taken into account as well to really know. Yeah. Dr. Laird?
Okay, I'll take the privilege of asking the last question here. Did you observe any formation of a crust on either the till or non-till? And if so, what impact would that crust have on your latent and sensible heat flux in your system and on the albedo of
Yeah.
the system?
Yes. Yes, we did observe at the non-till pretty early and later in the season that a developing crust to occur, and also at the till soil site we observed later in the season that our second period was around 63 days after the tillage event, and those substantial rainfall events occurred. That there was a crust that was occurring. We didn't measure exactly how large the crust was, but we do believe that too kind of could have also affected the evaporation later in the season. Don't know, can't say really if it was significant effect, but we do know that first of all, the crust at the till soil surface would definitely kind of affect the albedo because one thing that influences that why tillage usually kind of absorbs more net radiation because net surface aggregates form when you till the soil, and that creates the roughness, which kind of allows more radiation to be absorbed. So anytime you have a smoother surface, you're getting less net radiation absorbed right there, and being more deflected into the atmosphere. And so I think the effect of a crust, the main effect will be on the albedo, on whether or not it's absorbing or reflecting more or less net radiation due to a crust occurring. Yeah.
All right, well, let's see.